Write your name and seat number in the chat box. We will wait for 1 minute and we will start. Yes, we will start. So in the previous lecture, we learn about what is mean by coordination chemistry, what is coordination compounds, what is mean by ligands, what is Lewis acid, what is Lewis base interaction, how the complex is formed, then what is ligand, what are the types of ligands, monodentate ligands, and then polydentate ligands. Polydentate ligands again classified in bidentate, tridentate, tetradentate, depending upon the number of donor atoms they have. Now, we will discuss what is mean by charge number on the complex ion, charge number of the complex ion, and oxidation state of the central metal atom or ion. These are the two different entities. It is as for 1 mark. So directly, I am coming to the definitions. What is mean by this charge number? Charge number is nothing but whatever the net charge present on the complex ion. It is called a charge number. And how it is calculated? Charge number, it is nothing but it is the algebraic sum of all the charges carried by the metal atom and the ligands. So we will take the one example, then it will be very clear. So the complex is given here FeCN6 4 minus. This 4 minus is the charge on the charge number of the complex ion, because it is the net charge present on this complex. So we don't know the oxidation state of this Fe. We can calculate with this help of charge number. So what is the formula is given here? See the formula we have to remember only. Charge number of the complex is equal to net charge carried by the complex ion. Means whatever the charge present on the complex, it is called as charge number. And this charge number is nothing but it is the algebraic sum of oxidation state of the metal ion and total charges of the ligand. So this formula is important. By using this formula, you can calculate the oxidation state of the metal ion, and also we can calculate the charge number. So as the charge number is given here, so in the formula, charge number of the complex ion is written -4. See, we can clearly see here from where this value came, -4, because it is given -4. So put the value -4 in this formula. This is the formula. So -4 is charge number of the complex. So -4 is written. Then this is a oxidation state of the metal ion, oxidation state of Fe, we don't know the oxidation state of Fe ion. So it is written like this, oxidation state of Fe ion plus charge of ligands. Now you know how many ligands are there. 6 cyanide ligands are there, and this charge on cyanide is, you already know, it is a 1 minus. So in the next step, it is written oxidation state of Fe ion plus 6. This 6 is already given here. 6 cyanide ions are there, and charge of ligands, cyanide having the -1 charge. So 6 into -1, it is minus 6, and this -6, when it is comes to the this side, it becomes plus. So -4 plus 6 is equal to +2. It is a simple numerical process, and we get +2. This +2, it is the oxidation state of the metal ion, and it is always written in Roman digits in bracket. So Fe2 plus or Fe2 plus can be written like this. Fe2 plus, this Fe2 plus, it is the oxidation state of Fe. So by using this formula, you can calculate the charge present on the complex ion and also the oxidation state of metal ion. Don't worry, this is not as for exam, but you need this charge for naming nomenclature system. For nomenclature system, we require this oxidation state, and this charge is required. So this is the same as in 11th standard we learn how to calculate the oxidation number. It is same like this. So make a practice at your home. If you didn't understand this step, you can call me. Again, I will explain, because this example I have given in detail also. In detail, I have explained this example. Then the next is a very important, very important coordination number of the central metal ion. Now this coordination number is different in case of monodentate ligands and in case of bidentate ligands. Remember, number of ligands attached to the central metal atom or ion, it is called as coordination number. But this definition is applicable only in case of monodentate ligands. And how to identify whether the ligand is monodentate or bidentate? You know, when only one donor group is there, it is a monodentate ligand, and when two donor groups are there, it is called as bidentate ligand. So we will take one example here. See, in the square bracket, it is a cobalt is written. It is a central metal atom, and see how many ammonias are there. 4 ammonia molecules. These are the ligands, and 2 chlorine. These are also the ligands. So in case of this ammonia, one nitrogen is donor atom. In chlorine itself is a donor atom. So the total number of ligands are there 4 plus 2. These are the 6. Total 6 ligands are there. So the coordination number is 6. When this is applicable, when this definition is applicable, when these ligands are monodentate. So in monodentate ligands, it is very easy to find out the number, coordination number. Whatever the coordination number, it will be the total number of ligands. If the 6 cyanides are there, it will be the coordination number will be 6. But in case of bidentate ligand, I am coming to the bidentate ligand. You know the definition of bidentate ligand. It is having the 2 donor groups. In case of ethylene diamine also, there are 2 donor groups, 2 amine groups are there. And in case of this C2O4, 2 minus, 2 oxygens are the donor groups. So in case of bidentate ligand, the method of the calculation of a coordination number is quite different. The definition is whatever the electron pairs involved. In case of C2O4 2 minus, 2 electron pairs are involved, and in case of ethylene diamine also, the 2 electron pairs are involved in one ligand. If the one ethylene diamine is there, there are 2 electron pairs. If one oxalate ion is there, there are 2 electron pairs. If, see this complexes are given here, Fe in bracket C2O4 3 means how many oxalate ions are there? There are 3 oxalate ions. One oxalate ion having the 2 lone pairs. And 3 oxalate ion means there are 2 plus 2 plus 2. There are 6. 6 electron pairs are involved for the bonding. So the coordination number in case of bidentate ligand, it is 6. In case of this COEN thrice, one ethylene diamine having the 2 electron pairs are involved. But as there are 3 ethylene diamines, so again the coordination number is 6 here. See, we have to identify whether the ligand is monodentate or bidentate. If monodentate ligand is there, there is no question of electron pair. Directly we have to do the addition of ligands. 4 plus 2, it is 6. But in case of bidentate ligand, and how to identify bidentate ligand, already I explained. We have to check whether how many donor groups are there. In case of oxalate, you know, 2 oxygens are the donor pairs, and in case of ethylene diamine, you know, 2 amines are the donor pairs. So this may be asked for 1 mark, identify or what is the oxidation number, sorry, oxidation number ni, what is the coordination number of the complex. It may be asked for 1 mark only. So I have given the 2 examples. I think it is clear. So what is the coordination number in case of bidentate ligand? It is the definition is given here. The coordination number of a central metal ion in a complex is the number of donor atoms directly attached to it, or the number of electron pairs involved in the coordinate bond. First, half part of the definition is for the monodentate, and the remaining part of the definition is for the bidentate ligand. So general definition is prepared. What is the coordination number means is the nothing but the number of ligands. The number of ligands, the donor groups attached to the central metal atom, or the number of pairs involved in the coordinate bond. This number of pairs, number of electron pairs is applicable only for this one. The number of electron pairs involved in the coordinate bond, it is applicable to the bidentate ligand. So coordination number is different for monodentate ligand and bidentate ligand. Remember, for monodentate, it is nothing but the total number of ligands, and in case of bidentate ligand, it is how many electron pairs we have to, how many electron pairs are involved. If one bidentate ligand is there, there are 2 electron pairs. Then 2 bidentate ligands are there, there are 4 electron pairs. If 3 bidentate ligands are there, there are again 2's are increased. So 2 plus 2 plus 2, 6. And the shape of the complex is depend upon the coordination number, remember. So this is very important thing. If you wrongly calculate the coordination number, then the shape will be wrong. So this table, one table is shown here. What is the coordination number and what is the shape? If the coordination number is 2, then the shape of the complex will be linear. If the coordination number is 4, then the shape of the complex will be tetrahedral. If the again there are 2 shapes, tetrahedral and square planar for the coordination number 4. Then if the coordination number is 6, the shape of the complex will be octahedral. In the next part, we will see these all tetrahedral complexes, then square planar complexes. What is the difference between this square planar and tetrahedral? Also, we will see in the next slides. And if the coordination number is 6, the shape of the molecule is octahedral. So 1 mark question will be asked on this slide. So I try to explain at a glance. At a glance, we can remember what is the coordination number of the central metal ion. Then what is mean by double salt and coordination complex? In 2013, this question is asked for board exam. Write the difference between double salt and coordination complex. See, there is a simple thing I will explain. There is only one difference: double salt and what is mean by coordination complex. Already you learned about this coordination complex. Now I will explain what is mean by double salt. A double salt is a salt which is prepared by using 2 salts. For example, one is more salt. More salt, it is a in 11th standard, I think, for the titration purpose, it is called as ferrous ammonium sulfate. Ferrous ammonium sulfate, or it is also called as more salt. I think this is a sorry, not used, but for 12th standard we are using this Morse salt. Morse salt is a double salt. It is prepared with two salts. See the formula of the Morse salt. It is prepared with ferrous sulfate and ammonium sulfate. Equal amount of ferrous sulfate and equal amount of ammonium sulfate is mixed together and in hot water. This is heated after heating, after crystallization. This method is, this Morse salt preparation is also included in the practical also. So in the practical, we will prepare this Morse salt also, and for the titration also, we can prepare this Morse salt. So remember, this Morse salt is also called as ferrous ammonium sulfate, FAS. The short form is ferrous ammonium sulfate. Remember this formula. This formula, it can be asked for 1 mark, FeSO4, then NH4 twice, SO4 dot 6H2O. This formula can be asked for 1 mark for the board exam. Remember this Morse salt, it is also called as. Why this is a double salt, I will explain. Because when this Morse salt is dissolved in water, what is happening? See. So this is a Morse salt plus water. So Fe2 plus ion will be prepared, then ammonium ions are prepared, then SO4 ions are prepared. So they dissociates and the ions will be prepared. But in case of coordination complex, such type of ions are not formed. See, this is the difference between double salt and coordination complex. When the double salt is dissolved in water, this such type of ions are prepared. But if the coordination complex, if it is dissolved in water, such type of ions are not prepared. We will take another example of double salt. It is a carnallite. It is a salt of KCl and MgCl2. Again, these are the two salts mixed together, magnesium chloride and potassium chloride. And this is the formula. This can be asked for 1 mark. Write the formula of carnallite. For 1 mark, they can ask this question. Write the formula of the carnallite. It is a double salt. Double salt means it is prepared by using two different salts. So the carnallite, it is prepared with potassium chloride and magnesium chloride. When it is dissolved in water, again these ions are formed, potassium ion, Mg2 plus ion, 3 chlorine minus ions. So I am coming to the coordination complex now. Now whatever the group which is involved in the square bracket, it is called as coordination sphere. See, this is a tightly bonded, we cannot separate it, but these are the counter ions can be ionizable. So the difference between double salt and coordination complex is, when this double salt is dissolved in water, we get the ions, but when the coordination complex is dissolved in water, we will get only the counter ions will be ionizable. This C, this 4K plus means which are outside the square bracket, only these are ionizable. So the complex will be ionized like this. This is a counter ion 4K plus aqueous, and this square bracket remains as it is. Means this square bracket we cannot, what we can say, we cannot separate and we cannot prepare the ions. So this is the difference between double salt and coordination compound. Remember, the complex ion which is remains as it is because it is very tightly bonded, and these counter ions which are ionizable. Then Werner's theory, this is as for 2 marks. Make a mark in your notes also, or write in your notebook also, or whatever you are writing. I don't know where you are writing this or not, but this is a Werner theory. It is as for 2 marks, remember. This Werner is the name of the scientist who studied first the different coordination complexes. So the first attempt, it is made by the scientist Werner to explain the nature of bonding in coordination compounds. And this Werner is also called as the father of the coordination chemistry, because he studied many coordination compounds and given his theory. So what is his theory? I will explain in detail. Postulates means these are the findings of the Werner. So what is finding number one? It is also called as postulate number one. Say Werner, according to the Werner, metal in a complex has two types of valencies. Metal, which is a central metal to which different ligands are attached, it is having the two valencies. One valency is primary valency, which is ionizable, and secondary valency is non-ionizable valencies. This is given by the Werner. Then what is the second finding? Primary valencies are ionizable. It is already written in brackets. So the primary valencies are ionizable, and these are satisfied by anions. Remember, these primary valencies are satisfied by anions. In modern terms, these are called as oxidation state of the metal. So in the modern terms nowadays, it is called as oxidation state of a metal. Oxidation state of a metal is due to the primary valencies. And see the finding number 3. It is related to the secondary valencies. The secondary valencies, these are non-ionizable. And these are satisfied by the neutral molecules or negative ions. In modern terms, we called it as the coordination number of the metal. So primary valencies are satisfied with anions. It is called as oxidation state of the metal, and secondary valencies are satisfied by the neutral molecules or negative ions. It is called as coordination number of the metal. Then the fourth postulate given by the Werner is primary valencies, and all the postulates are related to the primary valencies and secondary valencies. Primary valencies are non-rigid and non-directional, and the secondary valencies are rigid and also having the directional properties. Therefore, its number means coordination number. Remember, whatever the secondary valencies are related to the coordination number, and in the previous slide also we learned the coordination number is responsible for the shape of the molecule. So the secondary valencies are directional, and depending upon the coordination number of the metal, the shape of the, if the coordination number is 4, the molecule will be tetrahedral or square planar. If the coordination number is 6, it will be the molecule, the shape of the molecule will be octahedral. If the coordination number is 2, we already learned this table. See, this table is denoted, this table indicates the secondary valencies. Nowadays, these secondary valencies are also called as coordination number. So the shape of the molecule depends upon the secondary valencies. Then the postulate number 5 is in a complex there are two types of spheres. Already we know the coordination sphere is inside the square bracket, and outside the square bracket it is called as ionization sphere. It is outer sphere. So what are the groups which are present in a coordination sphere? We cannot separate easily. That's why these ions are not prepared. In double salt also I explained you what is this coordination sphere. Coordination sphere means the sphere which is in the square bracket, and outside the square bracket it is ionization sphere. Ionization sphere, the name itself suggests it is ionizable. See this example again, this example, this K4 FeCN6. The this is a square bracket which is a coordination sphere FeCN6. This cannot be removed. This is tightly bound, and this is ionization sphere outside the square bracket. This is ionization sphere. So all these ideas are given by the scientist Werner. So this postulate, any 4 postulates can be asked for 2 marks. Each postulate it is for 1 mark, and it is related to the primary valencies and secondary valencies. So read this Werner theory. This can be asked for 2 marks. Then, so in this example also it is given, this is a coordination sphere. It is a secondary sphere, and this is a primary valencies. These are the secondary valencies. Outside the square bracket it is ionization sphere. So experimental observations. According to the Werner, he also done some experiments. These experimental observations are very interesting, found by the Werner. See, By this experimental observation, we can find out the formula. Werner treated 1 mole of purple colored complex COCl3 6NH3. This is the Werner. What Werner have done? See, when Werner treated 1 mole of this purple colored complex, this is a purple colored complex with excess of AgNO3 produces, he found that 3 moles of AgCl precipitate. So with this 3 moles of AgCl, we can easily identify 3 moles of AgCl precipitate means there are 3 chlorine should be there outside the square bracket. If the 3 moles of AgCl precipitate by using this, this is a clue, this is a hint for us. If the 3 moles of AgCl precipitate means 100% 3 chlorines are there outside the square bracket, because these are ionizable. If these are ionizable, then the precipitate will be formed. So this shows that the 3 chlorine ions present in the ionization sphere. And further, Werner found that when the entire complex is heated with HCl, ammonia is not removed. So 100% this ammonia will be present in the coordination sphere. So this shows that now this by using this combination of 6 COCl3 and 6 CnH3, all the 6 ammonia should be present in the coordination sphere, and these 3 molecules, these 3 chlorine ions should be present outside the square bracket. How will you identify these 3 chlorines? Because 3 moles of AgCl precipitate. Here, if the 2 moles of AgCl will precipitate, then 2 chlorines will be outside the square bracket and 1 chlorine will be inside here. So, by using this COCl36NH3, we can clearly here write down. Sorry, 6 printing mistake is there. 6 ammonia should be there and 3 chlorine molecules outside the square bracket. 6 ammonias are written here. There is one typing mistake. Ammonia should be 6 and 3 chlorines outside the square bracket. So one example I have given, this problem can be asked for 1 mark. When 1 mole of green colored complex, this is a COCl3 and 4NH3. This is a combination. 3 chlorine ligands and 4 ammonia ligands are there. On treatment with excess of AgNO3, it is found that 1 mole of AgCl, 1 mole of AgCl, it is precipitated. So by this 1 mole of AgCl means 1 Cl should be outside the square bracket. And what is the formula? I have given this answer. So see this, out of these 3 chlorines are there. So the 1 chlorine is outside the square bracket. Why? Because it is precipitated. It is precipitated because this is ionizable in the ionizable sphere. And the 2 chlorines are inside the square bracket. These are non-ionizable, and all these 4 ammonias are inside the square bracket. So this is an experimental observation found by the Werner. So remember, this is IMP. This is IMP for your exam. The examiner can ask this question for 1 mark. He will give this sentence, 1 mole of they can, instead of this example, they can give the different examples, but any type of example is given, we have to check only how many moles of AgCls are precipitated. So jitne number of moles precipitated hai, that will be outside the square bracket, and remaining will be inside the square bracket. So inside the square bracket, it is a coordination sphere. It is also called as secondary sphere, and outside the square bracket, it is a primary or ionization sphere. It will be ionized. So this Werner theory is the most important part I completed. It is many times asked for 2 marks. Ligands also asked for 2 marks. Then I'm coming to the next part, the classification of complexes. Classification of complexes, this is classification based on the types of ligands. Types of ligands, there are 2 complexes. So this is asked for 2 marks. Homoleptic complexes. So what is this homoleptic complexes and one is heteroleptic complexes? We will discuss after this homoleptic complexes. So what is this homoleptic complexes? Homo means this is same. One type of ligands, when one type of ligands are attached to the central metal, it is called as homoleptic. See this example. CONH36, only one type of ligand is there. Only ammonia ligands are there. So it is a homoleptic complex. Only one type of ligands are there. And in case of heteroleptic complexes, see, there are more than one type of ligands are there. See this example and compare these two examples. In case of the CONH36, only one type of ammonia ligands are involved, but in this example, we can clearly see four ammonias are there, also two chlorine ligands are there. So there are different types of ligands. Such type of complex are called as heteroleptic complexes. And when only one type of ligands are there, these are called as homoleptic complexes. So remember, for the board examination, 2-3 times this is asked. Write a note on homoleptic complexes and write a note on heteroleptic complexes. Only we have to write the definition and one example. Definition and one example. Homoleptic means only one type of ligands are there, and heteroleptic complexes means more than one type. It may be two types, it may be three types of ligands will be there. So in this example, there are four ammonia ligands and two chlorine ligands are attached to the CO. This is a CO is the central metal atom. So this is a very easy. Then classification of the ligands. Sorry, classification of the complexes on the basis of charge on the complex. If the positive charge is there, it is called as cationic sphere complexes. If the negative charge is there, it is called as anionic sphere complexes. And if there is no any charge, it's called as neutral sphere complexes. This is also asked for one mark for the example. Cationic sphere complexes. This cationic word indicates the positive charge is present. So see, the definition is given: a positively charged coordination sphere or a coordination compound having the positively charged coordination. It is one and the same. The positively charged coordination sphere is called as cationic sphere complex. See, this example is given. This is a coordination ion. See, the 2+ charge on the complex is 2+. That's why it is a cationic complex. Zn NH3 4 2+. Sometimes they will give such type of example. CONH3 5 ammonia ligands are there. One chlorine is inside the square bracket, and SO4. See, SO4, this is ionizable. SO4, these are ionizable. So this is how to identify this is a cationic complexes by using this. So SO4 will be ionized like SO4 2-. So automatically 2+ charge will be there on the complex. So this is quite little bit difficult to understand how this 2+ charge is there on the complex. So this, as this SO4 are outside the square bracket, it will ionize like SO4 2-. So the 2+ automatically the charge will be on the complex. So we have to only see the charge which is present on the secondary sphere. This is a non-ionizable sphere. It is also called a secondary sphere. Don't see the charge present on the ionizable sphere. So with the help of the charge present, we can easily find out whether the complex is cationic complex or anionic complex. Then ionic sphere complex, this is having positively charged, that's why this is cationic. The ionic sphere complexes means it is having the negatively charged. See, Fe, K, there is no any charge, but this is ionizable. It forms 3K+. So automatically the charge will be 3- on this complex. And in this example, NiCN4 2-, already the charge is given 2-. So if the charge is given, there is no problem to identify. But if the charge is not given on the complex, we have to check this K is positive or this SO4. See in this example here, the SO4 is a negative. Always when the right hand sides, ligands, these are the negatively charged, and when the left hand side, the left hand sides of the coordination sphere, these are positively charged. So this is a simple idea to identify this is positively charged or negatively charged. So whatever the ligands which are right hand side, remember, right hand side of the coordination sphere or of the right hand side of the square bracket, these having always negatively charged, and when the left hand side, these are always positively charged. So there will be 3K plus, these are the counter ions, and the complex is anionic complex, because the charge present on the complex is negatively charged. When there is a positively charged, it is called cationic complex, and when there is a negative charge, there is a anionic complex. When there is a no charge, it is called as neutral sphere complexes. See, this example is given when there is no any charge. See, platinum NH3 twice Cl2 and NiCl4. This is a tetracarbonyl nickel. There is no any charge on the complex. Such type of complexes are called as neutral sphere complexes. So make a practice at your home. Cationic sphere complexes. Read this carefully and try to write these examples: positively charged, negatively charged, and neutral sphere complexes. So, and the next part is IUPAC nomenclature system. Tomorrow we will discuss, because it requires entire 40 minutes lecture. Sorry, not tomorrow. Tomorrow's lectures are cancelled because we are going to take the extra lectures of geography in the next week. So when the geography lecture is there, we have to join for chemistry and give this message to many students, because see, the strength of the student is only 26, and before this lecture 43 students are present. If you do such type of absentees there, we cannot understand this chapter. Remember, this is not very easy chapter. If you carefully listen, then it is very easy. But if the absent is there, I cannot do anything. So my kind request to all students, please join on proper time and don't be absent, because only I will share the notes and videos, whatever the exercises we have to solve at your home. But for the physical chemistry also, I will give the solved numericals also. And make a practice at your home. Daily read the whatever the part. Today I completed the many concepts of this chapter actually. What is ligands and what is coordination compound. See, once again, as only 1 minute is remaining, I will do the revision. This cisplatin can be asked for board exam. See, which drug is used for the treatment against cancer? This can be asked for MCQ also. This can be asked for 1 mark also. Means only if you attend the lectures, you will get good marks. कुछ दूसरा मटेरियल पढ़ने की भी आपको जरूरत नहीं है. What is Lewis acid interaction, Lewis base interaction? So it's my kind request to all the students, please don't be absent for the lectures. What is ligands? So whatever the taught part, I can set the question paper of 7 marks. So entire chapter is not completed. Whatever